No announcements today, other than to remind you that there's a homework due tonight. And again, please submit contest spots so that we have something to do on Monday. Yes. It doesn't show up on the rankings, so there's okay. This is being worked on now, and hopefully will be resolved by the end of lecture. So yeah, sorry. If it's just not showing up on the rankings at all, you should resubmit it. Other questions or bot issues that people are having? Yeah.
You can resubmit it many times, right?
Yes. Yeah. Anything else? Okay, so today's lecture is on neural networks, and this is actually the last of the kind of content-carrying lectures in this class. So everything that we're going to cover today is going to be on the exam and all that. And then what we're doing tomorrow and then again on Monday next week is just talking about kind of applications of AI, things that you can do with the tools that we've developed in this class, and places you can go next, both at Berkeley and in your life, if you're interested in exploring AI more. So this is, we're kind of coming to the end here. So let's jump right in. What we're mostly going to be concerned with today is kind of developing this notion of learning nonlinear decision rules that we started to work on last class and the class before. So you'll remember, just as a sort of quick recap, the kinds of linear models that we've developed that look that have decision rules that look like weight vector dotted with an input vector are really good at learning linear separators on data like this that's maybe one-dimensional data where you can just drop a separator down the middle. We have good algorithms, things that work well, things that will find a sort of the best possible separator as long as one exists. Where these tools start to break down is in cases where the data is not linearly separable, like we have here, where we have a bunch of sort of red points on one side, red points on the other side, and blue points in the middle. And in these cases, just learning a linear classifier that acts on only the input features that you're given is just not going to be able to do anything kind of meaningful on this data set. And so the trick that we started developing last class was to, last class and the class before, was to map our data into some kind of higher dimensional space, right? So we start with some input feature that we're going to call x0. And we said what we're going to do either explicitly or implicitly by way of a kernel function is to transform this into a new feature vector that's not one-dimensional but two-dimensional that has features x0 and x0 squared. And when we plot these two-dimensional features now, we wind up with something that looks like this. And in this two-dimensional space, our data becomes linearly separable. And so in order to do this, again, either explicitly by writing this down or implicitly using some kind of like dual perceptron and kernel function, we in any case need to know ahead of time what our feature representation or what our kernel is going to be. And so it's very easy to spend a lot of time kind of sitting around thinking about the right way to choose these kernels or choose these hand-specified extra feature functions in order to make our data linearly separable if it doesn't start out as linearly separable. So yeah, just to put this another way, this same trick works in 2 dimensions, the same trick works in n dimensions. If we start out with data here that's kind of red in a circle in the middle and blue around it, we can project that into 3 dimensions, again, maybe using some kind of quadratic operation such that it becomes linearly separable in the higher dimensional space. And notice that if we kind of project back down what the decision boundary we have in the higher dimensional space looks like, it will correspond, depending on our choice of feature function, maybe to some kind of circle or some other nonlinear decision boundary in the lower dimensional space. So how do we know what features to design for our task? Well, one thing we can do, and we're going to look at a concrete example of this for another vision task in a minute, but is sit around dreaming of things that we think might be useful for some kind of classifier. One of the dangers when you do this is that it's not always easy to tell whether the features that you've invented are good features or bad features just by looking at how well your model is performing on the training set. And the reason for that is basically that if I add more and more features, I can only make my sort of the quality of my classifier on the training set improve, right? I can never hurt myself on the training set by adding more features. And to see this explicitly, if we step back to this slide, right, suppose my data starts out looking like this, starts out looking linearly separable. And I do this quadratic transformation that I was doing before anyway. I map these all into 3 dimensions like this, or to 2 dimensions. If the data was linearly separable in 1 dimension, it's definitely linearly separable in 2 dimensions. I just set all of my new feature weights equal to 0. I keep around the old one, and things are still working. So I can only ever do better by adding more features. And so the risk that you run is that by adding more and more features, you're going to start overfitting on the training set. The only way to really tell this is by, if you're considering multiple sets of features or how many extra features to add or whatever, the only way we can really assess this is by seeing how our model performs on some kind of held out data. So something to keep in mind when we're doing this sort of manual feature design process, and in fact when we're doing automatic feature design, which is mostly what we're going to be developing today. To start by talking a little bit about what manual feature design looks like, because this is something that's still important, especially on applications where we don't have a ton of training data to begin with, let's look at a concrete example. So suppose we're trying to do some kind of image recognition task. So I'm going to start with a photo that looks like this, and I want to figure out what this is a photo of. Is this a photo of a person? Is this a photo of a dog? Is this a photo of a skyscraper? And maybe even at some higher level of resolution, like what is the person doing? And if we kind of think about intuitively what the right way to do this is, and what the right way to get a set of features that our model is going to be able to work with, one question we can ask ourselves is, what's the kind of least amount of information that I could extract from this image that would allow me as a person to figure out what's going on here? And so one thing that we can notice is that, the colors and the color of the sky and the lighting conditions and the shading on the guy's leg depending on where the sun is or whatever, none of this really matters. And I would be able to do just as well at this task if I only had access to a kind of line drawing of the image. If I only had, basically, if I knew where the edges were in the image and where those edges were in relation to each other. And so one image preprocessing thing that we can do is we can start with this raw pixel representation, and we can map from that raw pixel representation into something that kind of discards all the color information, discards all the shading information, and just keeps around pixel by pixel whether that pixel lies on some kind of edge in an image or not. And so this is like a preprocessing step, a sort of computer graphics step that we're going to do first in order to get better features. And we hope that these features will be sort of more generalizable and also make it easier for our model to actually find the linear separator if one exists. And so we have this edge representation of our image, and then we say, well, maybe even knowing kind of pixel by pixel whether it lies on an edge or not is more information than we actually need, because I expect my classification decision about this thing to be invariant to, if he moves his arm a little bit to the left or the right, or if he sort of moves his legs a little bit. So all we really need to know is kind of like, are the edges sort of arm-shaped in this region of the image? Are the edges sort of leg-shaped in this region of the image? Are the edges sort of head-shaped in this region of the image? And so what we wind up doing is, or one thing that we can do is to break the image up into a bunch of much coarser grid cells that kind of look like this, and then in each grid cell, just saying, of all the edges that I can see, how many of them are pointing in this direction, how many of them are pointing in this direction, how many of them are pointing in this direction down here maybe, and so on. And so what you wind up with is some kind of representation of your image that looks like this thing right here. This is generally referred to as a histogram of gradients, or Hogg representation. And just to persuade you that this is in fact a sensible thing to do, here is what one of these Hogg representations looks like that we can extract from a natural image. And sort of the way to interpret what's going on here is that for each of these cells, we basically have 8 features for each of the 8 coarse directions that the edges might be pointing, and the brightness of those lines corresponds to the strength of the feature weight there. What is this a picture of? A bicycle, right? And so here's the thing that we actually computed it from. And so the point is that this thing, weird as it is, basically captures most of the information that you need to figure out what is depicted in this image, but it's a much lower dimensional representation of that, and the sort of dimensions that we've created, the features that we've introduced, are maybe more useful, more rich, and easier to figure out with a classifier. And so this is just to persuade you, basically, that doing this kind of feature design and trying to learn a linear classifier on this representation of the image, rather than on this representation of the image, which is just RGB values for every pixel, is something that's going to be easier for us. Are people basically persuaded of this? Okay, cool. So on one hand, this is great because we now have a better feature representation of our image. But on the other hand, we had to do a lot of work to get this hog thing, and we, are knowing what we know kind of about the structure of vision problems in general, and about the structure of the visual system that allows you to make these kinds of classification decisions. And all of the work that we put into developing this histogram of gradients representation is not going to port to any other kind of classification task that we want to do outside of vision, right? Spending a lot of time thinking about these hog features doesn't tell us anything about how we're going to solve spam classification or anything about this medical diagnosis task that we talk about occasionally. And so kind of the state of machine learning until pretty recently was for a lot of these application areas like language or like vision or like robotics. A lot of the work that people did was developing better and better feature representations that kind of captured the structure of that particular domain or that particular task that we were trying to solve. What we would really like is, rather than having to do all of this manual feature design, if we could actually allow our models, allow our machine learning procedures to invent good features for us in the same way that they are able to invent good classifier boundaries for us. And so what this is going to look like in particular, right, we kind of know the right way of expressing for ourselves the decision function that we want is some kind of linear operator on some set of features. But what we would really like is for those features, rather than us having to compute them directly for the image, to have those sort of automatically computed, and maybe automatically computed using the same kind of process that we're using to do this classification decision itself. And so this idea of letting the model learn features for you, in addition to learning the decision boundary, this class of models is called a neural network, and the sort of approach generally is sometimes referred to as deep learning. So let's talk about how that actually works. And perhaps unsurprisingly, it's all going to come back to the humble perceptron. So if you remember when we developed perceptrons before, this is just some kind of linear model that's going to start with a bunch of feature values that we've called here F1, F2, and F3. In this perceptron, each of those input features is associated with some kind of weight, which we've got W1, W2, and W3. We take each feature value, we multiply it by the associated weight, we add all of these things together, and that's going to give us what we called an activation before inside here. And then we look at that activation, and if it's greater than 0, we're going to output a positive label, and if it's less than 0, we're going to output a negative label. But the kind of fundamental operation performed by a perceptron is some kind of dot product between weights and features, followed by some kind of transformation function, which maybe takes me from that dot product onto labels, or as we're going to see, can do kind of arbitrary things to that dot product. All a neural network is a stack of perceptrons. A bunch of perceptrons sort of chained together either in series or in parallel. So here's something that's sort of commonly referred to as a multi-layer perceptron, which is kind of the simplest kind of neural network we can imagine. And as you can see, it works in basically the same way, right? So we have here, here's one perceptron, and here are the weights coming into it for each of these input feature values. We have one associated weight in this perceptron. We add those weights together to get an activation. We pass it through some kind of transformation function, and what we get out is some kind of transformed output here. And if we look sort of downward in this network, we have exactly the same thing. It's connected to all of the input feature values, and the only way it's different from the first perceptron that we had up top is that the input weights themselves might be different. So we have one of these, which we're occasionally going to refer to just as a node in this graph, or a unit. We have 3 of these units in the first layer here. We have a whole layer of units, and each of these units has some kind of output. Remember, that's just the transformed activation from it. And rather than using these to make our classification decision directly, we associate each of these with its own weight. Again, take a dot product with all of those and that weight vector, pass it through some kind of transformation function, and that's going to be the prediction made by our network. And we can generalize this to much deeper structures, and so the reason this is called kind of deep learning sometimes is you wind up with these very deep stacks of perceptrons, essentially, where each of these units is arranged into a layer with a bunch of other units in parallel, and then these layers are stacked in series. And all of this gives us a sort of big complicated transformation from the input to the output. What do we get from working with, oh, sorry, was there a question in the back? Okay. What is the advantage of using a model that looks like this? Well, one thing we can do is just say, sort of empirically, how well do these perform relative to existing techniques? So here's a graph on a particular image recognition task of the kind that we were just looking at. That's been a kind of standard contest that I think Stanford has run for the last couple of years. Davis, your parents are calling you. I'm going to decline. No, it's fine. So here's this ImageNet recognition task. And, circa 2010, the best performing models were getting about 30% accuracy on this task. And if we look at the trend of the best performing model over time, it's not clear that things were actually getting that much better. One of the entries in this image recognition contest in 2012 was a neural network called AlexNet, which basically cut the error rate compared to all of the other models in half. This was really exciting. People were very surprised about this. And so sure enough, by the next year, everyone was doing neural networks except for this one person who was still kind of trying to do a classical vision approach. And poor them, if neural nets hadn't happened, they would have had the best performing system. But instead, the neural net stuff kind of beats the pants off of the old stuff. And we're now down way near the bottom of the error rate on this image recognition task. This has happened not just in vision, but also in speech. And so here is a kind of corresponding contest that has been run in speech recognition. And we can see in the last few years that the best performing systems based on neural networks are way better than the best traditional things that we were doing before. There's a ton of hype in the sort of news and the media around these kinds of deep learning approaches right now. And I think and a lot of this hype is actually justified, right? These are real results. These are real tasks that smart, serious people had been banging on for literally decades, using everything they knew about vision or everything they knew about speech. And we were able to kind of do much better, overnight in research timescales by adding these neural network things. So it's easy to get excited about the hype. But I think one thing that gets lost a lot when people talk about this these days is that a lot of these techniques are not new, right? It took very, very long for people to go from kind of having the idea of these perceptron models to what would happen if we chained a bunch of perceptrons together. And so all of this kind of learning machinery was developed in the mid-60s, 70s, and then kind of revisited in the 80s and 90s. And it just didn't work until very recently. Now, remember, there are three things that you need to kind of build a machine learning system. You need the software. You need to know what kind of model you're using. You need the data. And you need hardware to run it on. And it turns out that the thing that's really made the breakthrough in all of this neural net stuff is about the data and is about the hardware. And the kind of techniques that we're applying are mostly slightly improved versions of things that we've had around for decades. So something to think about here that in research in general, the bottleneck is often not our ability to be smart, but kind of the laws of physics and the amount of data that we're able to collect. So that's kind of the state of things right now. And I think the fact that we had all of these tools that we invented years ago just sitting around waiting to be used is a large part of the reason that we've seen this really rapid progress, because we were able to just kind of apply things out of the box and have them start working right away. Okay, so here is an n-layer perceptron network, which in general we're going to refer to as a neural network. Now, how do we know that this actually has more representational capacity than an ordinary perceptron? Maybe a better way of asking that question is, why is it, obviously I need some kind of transformation function out here to get me from the space of dot products to the space of hard labeling decisions. Why do I have these little transformer boxes everywhere else in the network? Yeah.
I'm not really sure about that, but if you weren't there, the end result would just be a linear combination of the original features, so it wouldn't make a difference if you have one perceptron or a layer.
Okay, yeah, so that's exactly it. The kind of I guess let's unpack this a little bit. When we have a big multi-layer perceptron like this, first we can notice that this is some input vector that's being multiplied by some weight vector, let's call it W1. This is multiplied by some weight vector W2. This is some weight vector W3. If we didn't have these transformations here, right, all of these activations that are coming out of these are themselves just scalars. We have a bunch of scalars in sequence. That's a vector. So really all we've done is we've taken our input vector F and we've multiplied it by some weight matrix W. So we can think of kind of the parameters of each of these individual perceptrons, putting them all together, and we get a weight matrix like this. So if we didn't have these transformation operations here, then we have our first weight matrix, and then we're going to hit it again in the next layer with another weight matrix that we'll call W2. I'm going to run out of space. We have something that looks like this, W2 times W1 times F. And of course, we know just kind of by linearity, all I have to do is multiply these two things together, and I'll get some W prime times F. And so whatever model I had learned with these two weight matrices, I could equivalently express with a single weight matrix. And in fact, this is just going to be some kind of linear decision rule. And so the way we get around this is by adding these nonlinear transformations in the middle. We're going to be looking in some detail about how we choose these. But the key thing is that if they're not there, then all we've done is built a really complicated perceptron that at the end of the day is just doing a linear operation anyway. Questions about this? Okay, so how are we going to train this model? Can we use the perceptron update rule? Some nods. Who thinks yes? Who thinks no? Okay, what would it look like for me to apply the perceptron update here? Remember, it used to be that my weight vector and my x vector were the same shape. Right, x has n features, so I have one weight per feature, and so it's kind of well defined when I say w is going to be my old w plus x. Now I have a lot more weights than I have input features, right? My weight matrices are some bunch of big w things, and I just still have one input vector. So it's not even clear that it like type checks for us to say we're going to increment all of these weight vectors by some feature vector x. Because things are not the same shape anymore. So what other tool do we have for learning weights for models? Yeah. Gradient descent. So that's exactly right. Remember, what's coming out at this last layer here is some kind of prediction decision. And so we can define a loss on that prediction decision in the true label and just do gradient descent on this thing with respect to all of the parameters in this network. And so here's gradient descent again. And as a kind of practical note, most of the time these days people are doing some kind of momentum method to work with these things. But yeah, that's exactly it. So remember, for our ordinary perceptrons, we could sort of do the perceptron update rule because we have our weights here and we have our features here and we have the same numbers. But when we wanted to move to more general model classes and when we were looking at the things that we were doing yesterday, we found it easier not to kind of try to do some kind of local search using gradients and to do not this 0-1 accuracy, but some more complicated loss function. Yeah? So, right, the way we defined a perceptron was just to say we're going to take this dot product between W and our features. And then we said, if this is greater than 0, so in the binary case, right, if this is greater than 0, we're going to predict the class 1, and if it's less than 0, we're going to predict the class -1. So it's just taking us from the space of real numbers into the space of classes. But what we saw yesterday is that this thing is not really differentiable. A new version of Java is available. No. How do I get this back? Come on. Okay. Yeah, so what we saw before is that if we kind of want to use this as our loss criterion, you get this weird steppy objective surface that you can't do gradient descent on. And so we defined a bunch of other other loss functions that we could use instead that were going to be more amenable to doing gradient descent. So what would be a better loss function to use for training our neural nets? What's it look like? Yeah, it looks like a hinge, right? So the hinge loss, which looks like this, and that's definitely something that we could do. One thing that actually gets used a lot in classification problems that we kind of touched on yesterday, but we're going to go into more detail today, is to say, let's give the outputs of our network some kind of probabilistic interpretation. So rather than just predicting what's the single best label, let's predict a distribution over all of the labels. And so all we need to do is figure out some way of taking these scores that we get from the dot product in the last layer of the network and making them look like a probability distribution. And we're going to do that in, what is in some sense the easiest way possible. These scores might be positive or negative. If they're going to be probabilities, they have to be positive. So we're just going to exponentiate them like this. And now we have two positive numbers. They don't sum to 1 necessarily. We want our probability distribution to sum to 1. So we're just going to take these two numbers and we're going to normalize. And so this gives us an output from, maybe our perceptron if we have a perceptron, maybe our deep neural network if we have a deep neural network, that looks like this. So we have our weights for the last layer, and then rather than doing this thing that we've been calling greater than 0 question mark, we are going to apply this transformation instead, which turns those weights into a distribution over labels. And so we can now think about this in probabilistic terms, and just like we did with naive Bayes models, we can say, okay, now let's try to maximize the probability under this model of the data set that I've been given. Maximize the conditional likelihood here, which is the probability of the correct labels given their inputs that look like this. And so this is sometimes called the softmax function or the softmax loss. It's going to have the same properties as the hinge loss in the sense that it gives us partial credit for answers that are partly right? If I give some kind of small probability to the wrong answer, I can see that increasing that probability a little bit, even if it's not my favorite answer, is going to increase the value of this objective. And so, in practice, what we're going to do is we're going to minimize the negative log likelihood. Do people understand what we've done here? Question? What is W? So remember in our kind of ordinary perceptron, this is just the vector of these weights. And so this, this softmax loss here is well defined as a training objective for an arbitrary linear model of the kind that we've been looking at in class so far. But we can also sort of bolt it on as the very last layer of a deeper neural network, and it'll have the same properties that it gives us partial credit for putting some probability mass on the right answer. Other questions? Okay, so we're going to swap that in, and if you plot this function that we've drawn, it looks something like this. So now we have a network that looks like this. What's going to happen when I try to run gradient descent on a network that looks like this? Remembering that we still have these test if greater than 0 boxes in all the intermediate layers.
You're still going to have issues with continuity and like applying the gradient on that greater than equal to function. You're going to just have a ton of trouble when you're thinking about propagating the change backwards.
Exactly. So we saw that using this at the output layer was going to give us trouble at the output layer, that basically no change of the weights anywhere in the network was going to cause us to change our decision, so we weren't going to be able to see that it was possible to make progress. Now, if I wiggle these W's around, I'll be able to see how moving these W's affects my output. But what happens if I try to wiggle, say, this W33 down over here, when this little unit is doing some kind of hard decision at the output to transform that dot product into a 0 or a 1? Well, probably what's going to happen is if I change this W33 a little bit on any input, a small change is not going to push the whole activation from this unit over the line from being negative to positive or positive to negative. So we can get gradients in this part of the network fine, but we're going to be in trouble if we try to get gradients in any of these because these intermediate units that we've defined have the same kind of differentiability problems that our original loss function had as well. So if we really want this thing to be trainable end-to-end, we're going to need to do this nonlinear thing, this kind of smooth nonlinear thing, not only just at the output, but also at all of the intermediate layers. And so what we wind up with is something that looks like this, and again, in a deeper network, something that looks more like this, where what we have is a repeated series of these units, which take a dot product with all their inputs, and then apply this squashing function, and we're going to do that everywhere. And so sometimes we write this in this kind of matrix language that we were using before as W times sigma, which is some kind of squashing function, times a different weight vector, times sigma applied to another weight vector applied to the input. And so this is kind of doing the same thing as our network here. What shape is this that I've drawn in red? Is it a vector? Is it a scalar? Is it something bigger? Yeah. That's a vector, right? So when we write this, we're saying we're going to apply whatever this squashing thing is element-wise to all the entries in the vector, and we wind up with some kind of squashed vector. So then this whole thing is also a vector. This whole thing is also a vector. If we want multiple classes out at the end, we sort of do the sort of standard multi-class thing that we've been doing with perceptrons, where we have a single weight vector per class, and we normalize across the scores from all the weight vectors. If we're just making a binary decision, then this last thing is maybe going to be a vector instead, and we'll just look at whether that value is greater than 0 or less than 0. Yeah. Right, so we said before that we have to do something nonlinear here. Or what we wind up with if we throw all of these sigmas away is just a bunch of matrices multiplied together, which means we're just going to have a linear decision rule. So we need to do something nonlinear to the outputs of each of these sort of mini perceptrons inside of our network. And so then it just comes down to what is our choice of function. One seemingly reasonable choice of function is this 0, 1 thing that we were looking at yesterday that says I'm going to produce 1 whenever it's greater than 0, and I'm going to produce 0 whenever the output is less than 0, or maybe I'm going to produce -1 whenever the output is less than 0. But this has the problem that it's not differentiable, so it's going to be hard to get gradient, or the gradient is 0 almost everywhere, so it's going to be hard to figure out how to change any of these weights in a way that makes progress on the objective. So all we need here is something that is smooth, or kind of smooth enough to mostly give us gradients, but also nonlinear. And so you actually, I mean, we're not going to talk about this too much today, but you have tons of different choices in what you plug in here. The standard nonlinearities that people use, there's one that looks like this hinge, there's one that looks like a kind of ramp that's the hinge, and then it flattens out again at the top. You can do smooth, soft versions of both of these things. I saw a paper once where they just did like x cubed, which is totally crazy and it shouldn't have worked, but it seemed to work pretty well. So, I mean, really, you can do more or less arbitrary things there, and a lot of what people do nowadays is just kind of playing around with different nonlinearities to plug in at this place in the network. And there isn't like a great theoretical reason why one is better than another. Other questions before we go on? Okay, so yeah, here we are. We've finally figured out how to build up some objective, which here is going to be a sort of log likelihood objective. And we've designed our network in such a way that whenever we change any weight value anywhere in the network, the output of this thing is going to change smoothly with changes in those weight values. And so we expect that we're going to have gradients everywhere, and now we can just do gradient descent in the way that we were looking at before. And so the only question that we have to answer is, how do I actually figure out what this gradient is? And so if you remember, when we were kind of looking at optimization generally and loss functions before, we assumed that it was easy for us to just look at the form of our model, right? Here's our whole model, the whole loss function with the model embedded inside of it. And we can figure out what the gradient of this thing is kind of by inspection, right? That it's going to be, yeah, like x up to sign in the region where we're making wrong decisions, and 0 everywhere else. So that's fine. In one of these deep neural networks, now we have an objective function that looks like this, like we were writing on previous slides. And I don't know, this is really scary, and I don't remember my high school calculus class, and I don't want to have to do this by hand, because it's going to be a lot of algebra, and then we're going to have to take that algebra, and we're going to have to implement it on the computer, and probably we're going to make mistakes in the algebra, then we'll make mistakes in the implementation. This is like actually what my life was most of the time before neural networks really became a thing, is writing down models, taking gradients of those models by hand, implementing them, and then figuring out what you screwed up. And one of the really nice things that's come out of this whole deep learning thing is that we've been forced to develop really good tools for doing automatic differentiation. And so what we're going to be looking at here specifically is a way of sort of generically computing gradients of big complicated functions that look like this, without having to do more than a little bit of math by hand. To do this, it's useful to take a step back and stop thinking about neural networks specifically and think more generally about graphs representing computations. So suppose I have some function of 3 variables, f of x, y, and z, and this f function is defined to be the quantity x plus y times z, right? I can write this function down as a graph, and it's a graph that looks like this, where first I have some plus operation that's going to combine my x and my y, and next I have some kind of times operation that's going to combine whatever the output of that plus operation was with my z input. I multiply those together, and I'm going to get my answer here. So if I plug in -2 for x, 5 for y, -4 for z, I can kind of pass these things along the graph. I can do the right operation at every step, and I will get my answer -12 out at the end. What we're interested in computing here are gradients of this output, or partial derivatives of this output with respect to each of the inputs, right? So if we were going to write down this computation graph for one of these neural networks that we've been looking at, it's going to have one of these kind of leaf nodes in the graph for every input feature that I see, but also for every weight, because those are kind of inputs to the computation. And most of the time, but not all of the time when we're working with neural networks, right, when we're training them, what we're really interested in is the sort of partial derivatives of this output with respect to each of these weight vectors, each entry in the weights in the network. So let's look at that specifically. What we're going to do here is we're going to start by introducing a name for this intermediate value here that we're going to call q. And so now we can write this original function f in 2 pieces. We can first say q is equal to x plus y, and then f is equal to q times z. And what I really care about getting out at the end are the partial derivatives of this sort of full function f with respect to each of the inputs here. The way we're going to do this is we first kind of propagated values forward along this graph, which we've drawn in green, and we're going to see that we can then get each of these partial derivatives by computing derivatives incrementally and propagating them backward along the graph in a way that looks like this. So we're first going to observe, well, a couple of things to observe. We're first going to observe that kind of locally for this q thing, the partial derivative of q with respect to x is 1, and partial q by partial y is 1. And similarly for this last multiplication operation right here, if we think of it just as a function of 2 simple arguments, we have partial f by partial q is z, and partial f by partial z is q. So in general, these kind of local partial derivatives might depend on some of the other inputs that we've seen. So now let's start walking backwards along the graph. We have here, kind of trivially, that partial f by partial f is equal to 1, and partial f by partial z is equal to q, right? This was something that we were able to read right off the form of f. And so we look at what q was on this original graph. We see over here that q is 3. So we're going to copy this 3 down here. So that's one of the things that we wanted to figure out, and we can kind of check that off the list because we've already computed it. Next, we're going to keep filling in this graph. And here what we care about is partial f by partial q. We know how to plug that in as well. That's -4. Remember, the -4 just came from here. In the same way we copied the 3 down, we're copying the 4 up. And here's where it gets interesting. What I want is partial f by partial y. And now I don't have an expression of that form anywhere in any of these kind of local partial derivatives. But I have the chain rule, and the chain rule tells me that I can express this thing as a product of two quantities that I do know. One, the gradient coming in from this direction, and one, this local partial derivative that I had previously computed for this particular node in the graph. And so I multiply these two things together. That's going to give me this -4 right here. And similarly, I'm going to get a -4 up top for partial f by partial x. And all we're doing here, again, is the chain rule. To write this in much more generic terms, if I'm looking at some node in this kind of generic computation graph, and I want to figure out what the partial derivative, well, yeah, and what I ultimately want to figure out is the partial derivatives of some loss function that depends on z downstream with respect to x and with respect to y, I can decompose that into two pieces, one of which is the gradient of the partial derivative of this loss with respect to my output z, and one of which is the partial derivative of this function f with respect to the particular input to that function that I care about. And again, this is just the chain rule. And so if we want to do this for the whole graph, we can just keep repeating this operation all the way back. We've gone through this really fast. I would encourage you to kind of go back and review this again in the notes because it's hard to see the first time. But the key thing here to notice is just that we can basically do all of this computation in two passes through the graph. One in a forward direction, where we're computing each of the actual values that we need as intermediate results in our prediction, and then one in a backwards pass, where we start with partial derivatives of the output with respect to things that we computed late, and we can use those to compute partial derivatives with respect to things that were early on. And this is just an application of the chain rule. So yeah, to kind of, one thing to observe is that when things are branching, which in general is going to happen in these kinds of networks, we're just going to add the gradients together. So to implement this auto-differentiation procedure, in general, what I wind up with is some kind of pseudocode that looks like this, where, where basically I have a sort of generic computation graph. I'm going to do a forward pass by iterating over each of these things in order in sequence, and then doing a backward pass by iterating over those in reverse and doing some kind of backward operation and forward operation, where the forward operation is just the actual thing that I'm trying to compute, and the backward operation is taking the derivative that I'm getting in from above, taking my local derivative, multiplying those two things together. And that's basically it. Questions about this procedure before we go on? This is referred, and I should mention because this is important, this is referred to as backpropagation for reasons that are hopefully obvious. Question?
How does this connect back to the earlier graph with the multiple perceptrons?
Okay, so we can think of that earlier graph with multiple perceptrons as a special case of something that looks like this. Right, where what I really want here is a blank slide, and we don't have a blank slide, so I'll just draw it on the board. Right, but where in a kind of similar way, I can say I have my input x1, my input x2, my input x3. I have maybe my weight 1, my weight 2, my weight 3 up here. I'm going to multiply these things together, these things together, these things together. I'm going to add these up. And then I'm going to apply whatever this squashing function is that we were talking about before. And I know kind of for each of these operations locally how to compute the partial derivatives. And so I just build this whole huge graph for the whole neural network that we were looking at before, right? This thing here, this is one perceptron, or one unit in the graph, we want to start calling them now. And so I'm just going to make a copy of this thing for every one of those cells that we were looking at before, and then, you know, kind of for the inputs, they'll come together at these x's. For the intermediate ones, I'll take the output of this thing and I'll pass it further down until we get to some node at the very end that's computing the loss. And so it's just a big graph, and then when we're doing training, we don't actually care about the partial derivatives with respect to these guys. but we do care about the partial derivatives with respect to these.
Wait, sorry, could you say that last bit?
So when we're training, right, we want to, x is fixed. We don't get to move x around. And so what we really care about is getting partial derivatives of this loss function way over here with respect to the weights. And the weights are just going to live as leaves in this graph in the same way that other inputs do. One thing that's really cool about this, well, we're going to see an example of things that you can do with this. You can actually take derivatives of your inputs, or take derivatives of the loss with respect to your inputs, and basically say, like, if I had a picture, what would I have to do to this picture to make it look more like a cat? And we're going to see what happens when you do that. It's a little terrifying. Yes?
So we use the forward propagation to get the result we predict, and then we use the loss function to value the loss.
Right.
And then we, according to the loss, we use backward propagation to update the weights.
Exactly. Yeah, and so all this backward propagation thing is doing is giving us a kind of efficient dynamic program for computing all these partial derivatives, which is, you know, and we need these things because gradient descent needs these things. Other questions? Okay, so one other thing that I want to kind of touch on briefly here is that what we've looked at so far, come on, is what's typically referred to as a feed-forward neural network, which means that, and a kind of a generic feed-forward neural network, which, to come back to the slides, right, the set of weights that this thing has are different from the set of weights that this thing has, are different from the set of weights that this thing has, and kind of every one of these units, the weights are chosen sort of totally without respect to what all of the other units are doing, and we just do this one big forward pass, and everyone is kind of locally remembering their own weights. It turns out that for a lot of tasks, it's useful to impose a little bit of structure on the weights that the network is able to learn. And so one thing that we do in vision a lot is to say, kind of across space, we're going to tie these weights together. So we might say that this thing is going to look at, this is actually not an ideal diagram for this, but let's just draw this off to the side. So suppose I have an input image that looks like this. And so my features here, remember, are just pixels. And I'm trying to go from pixels all the way to a classification decision. And so if I'm going to make a sort of fully connected feed-forward network, I'm going to have all my hidden units, my little mini perceptrons up here. Each of these is going to be connected to all of the inputs in this image, and is going to have a totally different set of weights for operating on those inputs. It turns out that in really big images, this means that you're going to have a ton of weights, which makes the learning problem hard, and there's not a lot of kind of structure to this objective. One thing that we can do instead is to say, okay, you, unit number 1, you only get to look at this part of the image. And you, unit number 2, you only get to look at this part of the image. And you only get to look at this part of the image. Let's use a different color. This part of the image. You only get to look at this part of the image. So, you know, each of these things, rather than looking at everything, gets to be a kind of local receptive field. And then we additionally say that all of the weights for all of these things have to be shared. And so what that's going to mean, what that is going to mean essentially, is that we're starting with our input image. We've invented some kind of filter that we're applying to a bunch of local regions in that input image. And what we see at the very end is the response of that filter. And so doing this weight tying and restricting the set of things that these units are able to look at dramatically reduces the number of parameters in our model without necessarily sacrificing a lot of expressive power. And so that's something that turns out to be really useful for a lot of computer vision tasks. One of the cool things is if you go in and look at how the eye works, some of the things in the really early human vision system actually seem to work in much the same way, where you have these kind of tiled patterns of things. And if you look at the trained versions of these networks, and I think we'll see this in a minute, they basically learn reasonable filters like edge detectors or like corner detectors, and some of them become responsive to particular colors. And so what you wind up with are units that respond in useful ways to specific features. So that's one kind of pretty standard change we make to the generic neural network story. The other one, just to talk about it very briefly, is what's called a recurrent neural network, where now, rather than tying our parameters together in space, like we did for these vision tasks, we tie our parameters together in time. So we say the set of weights that take us from these the set of weights that take us from these activations here to these activations over here are going to be the same as the set of weights that take us from these activations here to over here. And this turns out to be really useful for a lot of sequence modeling tasks. So in language modeling, for example, or kind of things that we do with natural language generally, things that we do with time series, you can use this recurrent structure where you're tying weights together across time. And that's also just a useful structural bias to impose on the network. And you can kind of think of what's going on here as being very similar to a hidden Markov model, right? Where we say, we know that the actual kind of hidden state or our belief about the hidden state might change over time, but the rules that we use for updating that are always going to be the same. I think what would be most useful at this point is to just take a little peek at one of these things in action. So Google put together this super cool in-browser neural network demo. And so what we're going to do right now is we're just going to build a neural net, and we're going to train it, and we're going to see what happens. So what we have up here right now is a neural network with 0 hidden layers, which is to say just a linear model of the kind that we've been looking at in class so far. This linear model has access to 2 input features, one of which looks like this, and one of which looks like this. So this means that basically the things on the left, every point has an x value that's close to -1. On the right, every point has an x value that's close to +1. For our other feature, it's just the same thing, but rotated by 90 degrees. So every point on this grid here is going to have 2 of these features, one for this x1, one for this x2. How many weights is this linear model going to have, or are we going to need to represent it? Somebody please. This is just a linear model of the kind that we've been looking at all class. Yeah, 1. Okay. 2 features. 2 weights, right? 1 weight per feature. This is all very familiar. This is not a neural net. This is just a normal linear model. Do we think we're going to be able to correctly classify all of these points using a linear model? Yeah, right? Because they're linearly separable. So what we're doing here is gradient descent. And we run gradient descent, and almost immediately we correctly classify all of the points. And there's not much to see here. So we can look at the weight that the first feature gets, the weight that the second feature gets, and sure enough, the kind of in the top right corner where both of our features are large, we want our output to be large, so we have positive weights, and we wind up with a decision boundary that looks like this. Okay, let's look at another classification problem that looks like this. Do we think that our simple linear model is going to be able to classify these points? No, right? So let's look at what happens when we run gradient descent with this linear model on this set of points that we have. It kind of gives up, right? So we can look at this classification boundary. What is happening? Slack. Okay, sorry. I can't turn the volume off. So if we discretize the output, this is what the actual decision boundary looks like. But the model's very unconfident, and it's hard to see up here, but if you look at the loss, it's basically bottomed out at 0.5, and we're not actually classifying any better than random chance. Here. We can, here, I'll just do this. This is easier. Okay, so what we need is a neural network. So we're going to rescue ourselves by adding a neural net here. Let's add a single hidden layer with 2 hidden neurons, right? So 2 of these little units like we were looking at before. Who thinks that we are going to be able to classify this with this neural net that we have here? And who thinks we're not? Okay, so we have some neural net skeptics here. Let's see what happens when we run this. Okay, so we're not able to get absolutely everything right, but we're able to do pretty well. And what we can notice here, if we stop this, is that from these input features, we've created 2 intermediate layers, and one thing we can do is peer at these things and see what their outputs look like. And so here's one that is going to respond really positively to things in kind of the lower left region of space and negatively to things in the upper region of space. And here's one that's learned to distinguish between left and right and is responding positively to the things on the left and negatively to things on the right. And when we take a sort of weighted combination of these 2, and we then try to do a linear classification based on these features rather than our input features, we're able to do okay, right? We're doing a lot better than our simple linear model did. We've learned some kind of nonlinear decision boundary, but we aren't classifying everything else. We aren't classifying everything correctly. What should we do next? Add more layers? Okay, we can either add more layers or we can add more neurons. Let's start by adding more layers. So now we have something that looks like this. We're going to start it off again. And not so good, not so good. But, oh. Okay. It kind of seems to have bottomed out there, but maybe we'll run it for longer. One other interesting thing to notice is that we're pretty badly overfit, right? So these 2 training curves here, this shows our performance on the training set, and this shows our performance on the test set. We're about 13% worse on the training set than the test set because this random training set that we drew happens to have not that many points in this little part of the donut. But if we go over and look at our test data, we see that the test data has a lot more points in that part of the donut. So what the model has learned to do is basically hedge and say, well, if I have to be bad in some region, then I'm going to be bad in the regions where I don't see that many training points, and that turns out to be really bad at test time. Question? Okay, so let's look at the response of this thing, right? This has just learned some different linear boundary because it had only linear input features to start with. And so, for the same reason that we can only learn linear decision rules in a singular layer, the neurons in the first layer are only going to respond in a kind of linear way to our inputs. By the second layer, this is no longer true. And we can see over here that kind of in the top right corner, it's responding more positively to things right in the middle than it is to things far out on the side. Other questions about what's happened here? Okay, so that's adding more layers. The other thing that we can do, rather than making the network deeper, is to make it wider. So let's try that and run it. And there it is. So notice, before when we were talking about doing classification on data sets like this, we had to sit down and say, well, can I do this with a polynomial kernel, or can I invent some other extra features that are going to allow me to do this? And here, none of that. We just said, here's a neural network. Figure out the right set of features to feed into my final layer. That will allow me to make the correct classification decision. And you can see what it's done is it's basically learned to kind of fence off the blue things on the inside, and then a proper linear combination will allow me to put all these things together and get the right answer. Notice this is like definitely not a unique solution. We could permute the neurons, we could flip the signs of both this and then the weight coming out of it. And so one of the things that's really kind of interesting about neural nets from a theory perspective, and a question that we still haven't really figured out how to answer, these things have tons of local optima, way more local optima than most of the other model classes that we consider, because there are so many symmetries in the training objective, right? That I can always shuffle things around, I can always kind of flip signs and not change things very much. For reasons that are not super well understood, it seems to be the case that most of the optima that we actually wind up in are good enough relative to the global optimum, and this is something that's very mysterious and interesting, that's somehow related to the structure of the objective function, but we don't know how to make more precise statements than that. Okay, so let's look at one last super challenging data set. This is sometimes referred to as the Swiss roll. Who thinks we're going to be able to do this with one hidden layer and 4 neurons? One person. Okay, let's give it a try.
Not so hot. Yeah, so this is a really interesting thing to notice, is that in fact, these training objectives, and I guess we're probably not going to see it so much here, but tend to, let's see what the decision boundary looks like. So we have learned some kind of squiggly decision boundary, right? It's doing better than chance, and over time, it's improving a little bit, but it's getting there very, very slowly. So one other thing that kind of distinguishes neural nets from some of the other training objectives that we've been, or model classes that we've been looking at, and one of the reasons it took so long for us to discover that you can actually get good performance from these things is that they often have to train forever before you actually start to see meaningful improvements on your evaluation metric. Okay, I don't think we're going to do that much better with just these neurons that we have here. But we've definitely made some kind of progress here, especially on the training set. What I'm going to do is I'm going to stop this. I'm going to add, and notice we've done, 1,500 steps of gradient descent here. Let's add another layer, and let's add some more neurons to that layer, and then let's start this off. And let's sit here and watch it for a long time. Sorry? No, right? So this is the problem. We have to do all this computation. I can't figure out what it's going to come up to eventually because we can't analytically solve that objective. We are running gradient descent in the browser, and we don't know where gradient descent's going to go until we actually see where it winds up. Normally it has done something better by now. Anyway, notice here that we are learning all kinds of interesting features that seem to kind of get at the spiral structure a little bit. Oh, something seems to be happening down in the corner. Maybe not. Let's leave this running in the background and come back to it in a little while. Okay, so all we have left to do today is to show off tons of cool things that we can do with neural nets. So here are some examples of that. We were looking at this image recognition thing before. Image recognition was really the first big win and the thing that kind of showed us that in this wonderful modern era, we're going to be able to do well on all kinds of tasks where previously we had to design features by hand. And so here are some examples of an image recognition system in action. And you can see that, oh, come on. Whatever, I'm not going to be able to draw on the screen. You can see that here where we have like a mite being predicted in the top left, that not only does it correctly get that it's a mite, but the other classification, the other labels it wants to assign here are plausible ones. It says black widow, it says cockroach. For mushroom, we can also predict more specific kinds of mushroom like jelly fungus or gill fungus. And in general, do remarkably well at this image recognition task. I think this is now in a state where a kind of untrained human who sits down to answer all these questions will do worse than the best performing of our image recognition systems. Lots of other tasks that we can do in vision. We can not only sort of figure out what things are, but we can start to figure out where they're located in images, and we can draw bounding boxes around things that we care about, or even kind of whole like wiggly masks around the outsides of things. So we can say, for example, in this picture up on the top right, that there's a man. The man is above the horse is above the ground, the horse is next to a dog. And once you're able to look at an image and figure out not only what is in that image, but where, now we can start to use it for all kinds of real-world applications like self-driving cars. So a lot of these improvements that we've seen recently in computer vision have translated directly into improvements in the kinds of vision problems that we care about out in the real world, like when we're building self-driving cars and we want to figure out how far away things are from us, or whether that thing in front of us is a pedestrian or a shadow or whatever. And it's all using this neural net stuff that we've been talking about in class today. So yeah, lots of things we can do with convnets. We can do pose recognition. And where it gets really exciting is that it used to be that if I had kind of different pieces of my model structure, right? I had a vision part of my model, and I had a language part of my model, and I had a robot part of my model. I would have to explicitly come up with some kind of like discrete formalism for allowing all of those parts to communicate with each other. I would have to say, I see in this image that there's an object in this place, and this place, and this place, and then I'm going to do, you know, some kind of model-based reinforcement learning or whatever that knows how to deal with those discrete object predictions that I've made. What we can do once we have neural nets is we can just take all of these things and glue them together. So we have, well, here's a piece of a neural net structure that we know is good at figuring out vision things, whatever that means. And here's a piece of a neural net structure that's good at learning policies, whatever that means. We stick them together, and now we can play Atari games. And I'll bring up a video of this if we have some time at the end of class. But you know, we start to have a language for doing this kind of multimodal, multitask stuff and learning it in an end-to-end way just by hill climbing on our final loss function. So this is really exciting. We can use this to play games where there's a kind of language and action component. We can use it, skipping ahead a little bit, to generate captions for images. I don't know how many of you have seen this stuff before. It was in the New York Times a little while ago. But so, for example, bottom left here, we have an image of a bunch of elephants in a field, and we can write down a neural network that will automatically generate a herd of elephants walking across a dry grass field just by sort of doing the convnet part and then passing that into a recurrent neural network that's going to spit out words one at a time and basically make a sequence of classification decisions where it remembers what it's done in the past. So this is something that's really exciting, especially for those of us who kind of work in application areas, because now it becomes possible to do lots of other exciting stuff. We said when we were talking about this backprop procedure that we can get gradients not only with derivatives with respect to the weights in the model, and also derivatives with respect to the inputs themselves. That is to say, we can say, what would happen, how should we change this input if we wanted to change our classification decision? This is what happens when you do that. So what we have, the easiest thing to see up on the right here is we said, here's this famous painting, Starry Night. Cause my model to classify it as a dog by hill climbing on, sort of altering each of the individual pixel values locally to make it more probable that I get a dog classification decision out. And what you get is this like nightmarish thing where there are dogs on top of the building, there are dogs in the moon, there are dogs in the stars, because you can figure out kind of what you need to do to change the predictions that the neural net is making. And so this was this deep dream stuff that came out of Google. There's a bunch of other exciting art stuff that has a very similar flavor where you can say, here's an image, make it look more like X, where X is either a classification decision, or now there's this neural style transfer thing, which maybe some of you have seen. There's like a little phone app you can get that will, it's like the ultimate Instagram filter. It will turn, take a picture that you've painted, or that you've taken with your phone, and repaint it in the style of any artwork of your choice, because we can kind of extract the style part without the content part using neural nets. So these are some exciting applications. We're going to be talking about a lot more applications of AI generally throughout the rest of the next couple of days in this class. But here's a flavor of what you can do with neural nets in particular. Let's see how our model is doing here. Oh, the weights have changed a lot. And sure enough, it's doing something weird, right? It's still not great, but it's getting about 3/4 of the test examples and about, I guess, 6/7 of the training examples right, by learning this totally bizarre nonlinear function using a bunch of features that we would have never thought to invent by hand, except for maybe this one, which looks kind of natural and clean. So network by itself figured out what features it needed to use and has made kind of meaningful progress on this classification problem. Yeah, question? It probably would not have gone quicker, but it might have been able to learn a better output representation. Yeah. Let's see. I have no idea what this is going to do. It's probably going to take a long time to converge to anything meaningful. Right, so it finds the 50-50 answer more or less right away, and then it's going to sit there for a long time, probably, before it figures out what to do next. So there are a bunch of issues that come up in training these things that we haven't really talked about today. One of them is that if you're not careful about what sort of nonlinear squashing functions you use inside the network, the gradients, even if they don't vanish, will, don't go to zero totally, will get smaller and smaller the further you go back in the network. And so the longer it's going to take you to make progress on the objective, because your gradients are really tiny when you're sitting over here in this part of the network. Yeah, so, I guess the kind of dark secret of all of this is that we've given up having to invent features of our own. But what we have to do instead is go through this like mostly black magic process of figuring out what happens if I add more layers, or make my layers wider, or change the nonlinearity that I'm using, or change the loss function, or do other weird things with the architecture of my neural network. The good news seems to be that, oh yeah, see, now it's doing something. The good news seems to be that this process of sort of engineering your architectures rather than engineering your features seems to be either, a little easier for us to do, or at least easier for us to like try everything and run it in parallel. But it's harder to figure out why things work and why things don't work when you're kind of in the middle of it. This is still doing worse than the other one was before, but maybe that'll change. Other questions? Or do you just all want to like stare mesmerized at it? I sat at my, oh. So here's another thing that can happen. If our step size is too big, it'll bounce around a lot. You remember that figure we had on the slides yesterday where we were jumping back and forth across that little valley? That's basically what's going on here. It's going crazy, probably because we made our step size too big. So we could dial down the step size up here, and that's another free parameter that you sometimes have to play with. This is bizarrely fun to watch. I just sat at my desk for like 45 minutes before this lecture playing with neural nets in the browser. Okay. Well, I don't know that we're going to do much better than this. So this is a danger of being too deep or too wide, is that these things can happen. But we're still doing pretty good on this roll thing. I once got it to correctly classify everything, but I can't remember how I did it. Yeah. Okay, and any other questions for today? Davis. Okay, so now please go out, do the contest. If you tried to submit before and submitted unsuccessfully, resubmit. And yeah, I hope you all come in for the remaining lectures. It's just going to be like fun looking at pictures of things like we did here and talking about things to do with AI. So see you tomorrow.